Okay, thank you very much for attending my presentation. My name is Shady Gomaa. I'm a postdoc at Northwestern University, working with Professor Gianluca Cusatis. My presentation today is about mechanical characterization of 3D printed ultra-high performance concrete. So in terms of background, as it was shown in the first two presentations, people usually use either large-scale testing to calculate the mechanical characterization of the material, or they can either cut or core samples out of 3D printed structures. So in our work, this work is good, but in our work we needed to go further in our analysis for mechanical characterization. So we wanted to overcome the shortcomings out of these two methods. The first method, in terms of large-scale testing, all the reported work in this part, which related to large-scale testing, had a lot of variability in the results, and that's because of different defects in the material related to surface defects, interlayer defects, or also the printing system. The second part, which is related to cut or core samples out of 3D printed structure, is we're going to eliminate the 3D printing features. So eventually we are converting the 3D printed element to kind of a cast element. So that's why we wanted to go a step further in this matter. So what we did, we wanted to capture the printing features effect on the mechanical characterization of the material. And this is not going to be easy, because if we wanted to test 3D printed structure keeping the surface, the printing surface features, then we need to provide appropriate loading conditions. And also we need to work on small scale samples first, then we can scale up. So we need to do this to deeply understanding the failure mechanism of 3D printed structures, to develop better printing methods and systems. And the second step is to calibrate and validate our computational models, which cannot be easily done using just experimental data. We'll need to do several trials to do it experimentally. So in terms of the experimental program, we have two steps to do this. The first step is to develop a nano-modified ultra-high performance concrete mix, and then we can do our mechanical characterization using uniaxial compression, split tension test, and flexure test. And as you can see here, I'm boxing printable UHPC mix based on our latest accepted paper for publication. We got to the point that we cannot say that we have a printable mix. This printable mix must be related to a specific printing system. So here, when we changed the nozzle shape from rectangular nozzle to circular nozzle, we got different shape stability. When we changed the extrusion system from piston type system to an auger system, we got different printing shape stability. So when we say that we have a printable mix, we need to relate this to a specific printing system. So back to, and also here, if you look at the effect of pumping, when we use different pump, the cavity pump versus piston type pump, we got the same mix to be printable using the piston type pump, which is no longer printable using the cavity pump. So that's why I'm boxing here printable, because it's printable for a specific mix, for a specific system. For the materials and the methods, we use the base mix of ERDC UHPC mix, which consists of cement, silica sand, silica fume, silica flour, and super plasticizer. Here I used the ADVA 190 to develop this mix, and then for sure we have water. We have a specific mixing procedure each time we perform this mix, and we use the rheological modifier to make it printable. We use the anti-gel 208, which is nanoclay with a percentage of 0.7 by weight of the binder material. And also in this work, we used some of the samples without fibers and the other samples with fibers. we use 2% volume by volume of the fiber. And eventually, when we use this nanoclay, we can see the difference in the slump height for the base mix and after using nanoclay. Slump table test is a good tool to judge if this mix is going to be printable or not. However, it's a simple tool. We have also done several good work in rheological characterization of this mix using different rheometers, but this is out of scope of this presentation. So I'm just showing the slump table test just for our reference. And as I spoke about the printing systems, at Northwestern, we have different printing systems in our lab. So in terms of automated machines, we have ABB robotic arm with 6 degrees of freedom. We also have a medium scale gantry with 3 degrees of freedom. And we recently got a large scale gantry with 4 degrees of freedom. For the extrusion system, we have an auger system, this type of system, and then we have a piston type system. And we have different pumps. We have a cavity pump, and we have a TK7 pump. And this is really powerful pump. I like it really much. It can pump the concrete really good. And the good thing about it is if you calculate the rheological behavior of the mix before pumping and after pumping, they will be the same. And thanks for Dr. Kusets to bring this to our lab. And then for the nozzle, we have circular nozzle, and also we have rectangular nozzle. So in this work, I'm going to present one printing system. I used the medium scale gantry with the piston type system and the rectangular nozzle with a width of 30 millimeter and a height of 12 millimeter. And this is a short video showing how the quality of our printing is. So here we printed 3 layers with a waiting time of 3 minutes between each layer. And the speed is 6.5 millimeter, I mean in length per second. And then after we print the 3 layers, we cut samples out of those layers and we performed our mechanical characterization. So the steps were print, move to the curing tank after 2 hours, and then cut samples based on the mechanical test that we're going to do. And here is the preparation of the sample. So since we want to keep the samples featured, we need to cap the material. And capping the material with the original method is not going to work because this is ultra high performance concrete. Usually we use sulfur, but the sulfur capacity is smaller than ultra high performance concrete. So we're thinking about which material has higher strengths as compared to ultra high performance concrete, and eventually we got to the point, why don't we use ultra high performance concrete? So we're gonna use the same material for capping, but to use the same material is not going to be easy because this gap sometimes it's really small. So we need a more flowable version of our mix so that we can cap the material easily. So what we did, we changed the super plasticizer. In the base mix, we used ADVA 190. To make it really flowable, we used Sika Viscorite 2100. And it makes it really flowable. You can see here in the flow table, it's really flowable so that it can fill any gaps so that we can have a good capping and eventually have a good barrel and smooth surfaces for loading conditions. Okay, so this is the sample after printing. This is a scanned version of the sample using our 3D scanner. The longitudinal direction is our X direction, the lateral direction is our Y direction, and Z direction is the vertical direction. Let's look at some of the results. So when we look at uniaxial compression results for samples without without steel fiber. So this is unreinforced sample. We can see that we have a clear anisotropic behavior of the material, comparing between cast materials and cast samples and all other directions of loading in Fx, Fy, and Fz directions. And we have 3 edges. And by the way, in this experimental program, we tested more than 400 samples to ensure that we have a repetitive results. And when we look at the failure mode, the failure mode is cone failure, the nice cone failure without interlayer failure. Once we add fiber, also we still have the anisotropic behavior of the material, but the difference is we have a splitting once we add the fiber because we have a weak zone between the printed layers. And this is when we compare between without fiber, we can see that it's a cone failure here. When we look at the 3-point bending results, the capacity of the printed samples as compared to the cast samples are almost equal. And you can see also the failure mode is exactly at the notch. And then when we added fiber, now we can see that the printed sample has higher strengths as compared to the cast samples, and this is because of the fiber alignment in Y direction and in Z direction. And the interesting thing here is we have a separation in the layer. So here you can see a separation in the layer, in the first layer of the printed 3 layers, and that motivated us to start a new experimental program when we can quantify and enhance the interlayer properties using different methods. And that's what we are working on right now. For the splitting test, here we can see the qualitative geometric effects here. So the crack is in the middle, but also because of the printed layer feature, we can see that we don't have just one crack, we have multiple cracks. Those observations right now we are working on doing a numerical simulation of those observations to kind of understand more what's going on when including the printing features. Okay, once we add fibers, so here once we add fiber, however we are loading in FYA, which is this direction, we still have also failure in the interlayer in the other direction, which also needs to be understood numerically. Let's look at some conclusions. So in conclusion, we have a clear anisotropic behavior when we test the uniaxial compression samples. For notch 3-point bending and splitting, we have a clear, we have no significant effect from the interlayer bond. But once we add fibers creates weak zones in the interlayer, which alters the failure modes and the anisotropic behavior compared to unreinforced specimens. In terms of future work, we need to scale up. So we have this large mixer, which can be connected to the piston type pump, and then we can deliver the material to the extrusion system, and eventually we can print. Out of this, we printed slabs using the idea of laminates, where we can print in X direction, in Y direction, plus 45, plus minus 45, and adapt this for slabs, especially two-way slabs, which for sure will maximize the bending capacity of these slabs. So here the speed of printing is 50 millimeter in length per second, and I think we can also increase this printing speed. So before I end my presentation, I would like to acknowledge the team member working in this work, and also the funding from ERDC. And thank you for your attention, and I'm ready for any questions.